Have you ever thought about how much of what we know today was considered completely bonkers just a few centuries ago? Science is this incredible, ever-evolving story where new discoveries don't just add to what we know, they completely rewrite the rulebook. Today, we're diving into 10 monumental discoveries that absolutely wrecked old scientific beliefs. Get ready to have your mind blown. Let's start with a big one: the Earth-centered universe. For over 1,500 years, everyone from ancient Greeks to medieval scholars believed in Ptolemy's geocentric model. Everything the sun, the moon, the planets all revolved around us. We were the center of everything. It made sense, right? I mean, just look up. The sun does seem to move across our sky. But then, in the 16th century, a Polish astronomer named Nicolaus Copernicus came along. He proposed a heliocentric model, putting the sun at the center. It was a radical idea, so radical he waited until he was on his deathbed to publish it. It took another century and the work of Galileo Galilei and his telescope to really hammer the point home. Galileo saw Jupiter's moons orbiting Jupiter, not Earth. This was concrete proof that not everything revolved around us. Suddenly, our special place in the universe wasn't so special after all. This shift didn't just change astronomy. It changed philosophy, religion, and our very sense of self. Next up, let's talk about what things are made of. The ancient Greeks, particularly Aristotle, popularized the idea of the four classical elements: earth, water, air, and fire. Every substance was thought to be a combination of these four things. It was a simple, elegant theory that lasted for 2,000 years. But then came the age of chemistry. In the 18th century, Antoine Lavoisier, often called the father of modern chemistry, started doing meticulous experiments. He showed that water wasn't an element, but a compound of hydrogen and oxygen. He demonstrated that air was a mixture of gases. Through his work on combustion, he also disproved the phlogiston theory, which was the idea that a fire-like element was released during burning. Lavoisier's work laid the foundation for the periodic table and our modern understanding that matter is made of atoms and elements, not mystical essences. Speaking of atoms, for a long time, they were thought to be the smallest, most fundamental, indivisible particles of the universe. The word atom itself comes from the Greek atomos, meaning uncuttable. This idea, proposed by Democritus and later revived by John Dalton, was the bedrock of chemistry. But in 1897, J.J. Thomson was experimenting with cathode rays and discovered something shocking: a particle far smaller and lighter than a hydrogen atom, the lightest of all atoms. He had discovered the electron. The indivisible atom could, in fact, be divided. This opened the floodgates to subatomic physics. Soon after, Ernest Rutherford's gold-foil experiment revealed the atom was mostly empty space with a tiny, dense nucleus at its center. The simple, solid ball model of the atom was shattered, replaced by a complex miniature solar system, which would later evolve into the quantum model we know today. Now, let's jump from the very small to the grand scale of the universe itself. For most of history, including for scientific giants like Isaac Newton and even Albert Einstein initially, the universe was thought to be static. It was eternal, unchanging, infinite in space, but constant in time. This was the comfortable, predictable cosmos everyone believed in. Then, in the 1920s, an astronomer named Edwin Hubble made a groundbreaking observation. While studying distant galaxies, he noticed they were all moving away from us, and the farther away a galaxy was, the faster it was receding. The only logical conclusion was that the entire universe is expanding. This was a bombshell. If it's expanding now, it must have been smaller in the past. This observation led directly to the Big Bang Theory, the idea that the universe began from an incredibly hot, dense single point. The static, eternal universe was replaced by a dynamic, evolving one with a definite beginning. Okay, let's get biological. Before the 19th century, one of the most widely accepted ideas was spontaneous generation. This was the belief that life could just arise from non-living matter: maggots from rotting meat, mice from stored grain. It seemed obvious, but Louis Pasteur wasn't convinced. Through a series of brilliant experiments in the 1860s, most famously his Swanneck flask experiment, he proved that microorganisms were present in the air. He showed that if you sterilized a broth and kept it from being contaminated by airborne microbes, nothing would grow. Life, he demonstrated, only comes from pre-existing life. This discovery wasn't just a win for biology. It revolutionized medicine. It was the foundation of germ theory, leading to pasteurization, antiseptics, and saving countless lives by showing us how diseases actually spread. While we're on the topic of life, let's talk about how traits are passed down. Before Gregor Mendel, the prevailing theory was blending inheritance. It was thought that offspring were just a smooth blend of their parents' characteristics, like mixing two colors of paint. A tall parent and a short parent would have a medium-sized child. But this didn't explain why certain traits sometimes skipped a generation and reappeared later. Gregor Mendel, an Augustinian friar and amateur botanist, spent years meticulously crossbreeding pea plants. He discovered that traits are passed down in discrete units, what we now call genes. He found that these units don't blend, but are inherited in predictable ratios, with some being dominant and others recessive. His work, published in 1866, was almost completely ignored for over 30 years. When it was rediscovered, it became the foundation of modern genetics. Now for a shift in the very fabric of reality. Newton's universe. Isaac Newton's laws of motion and universal gravitation, published in 1687, were perhaps the greatest scientific achievement of their time. They described a clockwork universe, where the motion of everything from falling apples to orbiting planets could be calculated with perfect precision. Time and space were absolute, fixed backdrops for the events of the universe. This view reigned supreme for over 200 years. Then, a young patent clerk named Albert Einstein came along, in 1905, with his theory of special relativity, and later in 1915 with general relativity. Einstein turned everything upside down. He showed that space and time are not absolute, but are interwoven into a single fabric, space-time, and this fabric could be warped and curved by mass and energy. Gravity wasn't a mysterious force acting at a distance, but the effect of this curvature. Einstein didn't prove Newton wrong. Newton's laws are still a brilliant approximation for everyday speeds and scales, but he revealed a deeper, stranger, and more wonderful reality. Let's dig into the Earth itself. For centuries, people noticed that the coastlines of continents like South America and Africa looked like they could fit together. But it was just a curiosity. The scientific consensus was that the continents were fixed in place. In 1912, a German meteorologist named Alfred Wegener proposed a radical theory, continental drift. He gathered evidence matching fossils on different continents, similar rock formations, and climate data to argue that all the continents were once joined in a supercontinent he called Pangaea. But he couldn't explain how the continents moved. His theory was ridiculed and largely rejected by the geological community. It wasn't until the 1960s, with the discovery of seafloor spreading and the development of the theory of plate tectonics, that Wegener was vindicated. We now know that the Earth's crust is made of massive plates that are constantly, slowly, drifting on the mantle beneath. Back to medicine. For thousands of years, illness was often treated with a practice called bloodletting. The idea, based on the ancient theory of the four humors, was that sickness was caused by an imbalance of fluids in the body. Draining some blood, it was thought, would restore this balance. It was a standard treatment for everything from a fever to a plague, and it was practiced by doctors well into the 19th century. One of its most famous victims was likely George Washington. But slowly, a more scientific approach to medicine began to emerge. Physicians like Pierre Charles Alexandre Louis in France started using statistics to compare patient outcomes. They found that patients who were bloodlet were actually more likely to die than those who weren't. This evidence-based approach, combined with the rise of germ theory, finally put an end to this harmful practice and paved the way for modern data-driven medicine. Finally, let's talk about the brain. For a long time, the dominant idea was that the brain was a single, unified organ, with all its parts working in concert. But in the mid-19th century, a French physician named Paul Broca had a patient who could understand language perfectly, but could only say one word, tan. After the patient's death, Broca performed an autopsy and found specific damage to a region in the left frontal lobe. This region, now known as Broca's area, was clearly linked to speech production. This was one of the first strong pieces of evidence for localization of function, the idea that different parts of the brain have specific jobs. This discovery shattered the idea of a uniform brain and opened the door to modern neuroscience, allowing us to map out the intricate functions of this incredible organ, from vision to memory to emotion, from the cosmos to the continents to the very cells in our bodies. The history of science is a story of brave thinkers challenging the status quo. These discoveries weren't just updates, they were revolutions that forced us to see the world in a completely new light. It makes you wonder, what widely accepted facts of today will be the old science of tomorrow? Thanks for joining us on this journey through scientific history. If you enjoyed this, make sure to hit that like button and subscribe for more deep dives into the world of science. See you next time.